All right, so chapter 22, organic chemistry. We're gonna go over the basics of organic chemistry, including what organic chemistry is. We'll talk about isomers, and then we'll talk about some naming and the structural naming. So organic compounds is a bunch, and basically you have everything that's a hydrocarbon, anything that's a hydrocarbon, or what we call an organic substance, meaning it's the backbone of it, and most of the bonding, the covalently bound chains are carbon and hydrogen. So in this structure, these structures right here, you have cinnamaldehyde and vanillin, which are both aromatic structures, right? We call them aromatic. So that word aromatic, which we'll talk more about later, it comes from the word aroma, which means to smell. So a lot of these compounds in organic chemistry, a ton of them have aromatic rings, which are either 5-membered, 6-membered, 7-membered, or so forth, and usually not much more than 7, and mostly 6, like you see here. And these rings, they have several very important properties, and one of them is their property of they create a smell. Now, the way you read this is clearly the carbons are carbons, the hydrogens are hydrogens, but what about the vertices where there's no label there? So what, anybody know what the vertices are? Yeah. Yes, they're carbon. It's good. So vertices are carbon. And then, so let's take a look. Let's say we label these carbons. How many bonds is carbon supposed to have? Covalently. It could have a double. Yeah. No, but how many? Yeah. So how many total bonds is carbon supposed to have? 4, right? Good. 4 bonds according to our Lewis structures, right? So these carbons right here, the ones that are in this aromatic ring, how many do they have? They have 3, right? But they technically have 4, and the 4th one is assumed. So does anybody know what would you think that would be an assumed atom in this structure? Yes, Christina. Hydrogen. Yep, hydrogen. Good. So hydrogen. So we assume a lot of hydrogens in these organic structures. That's why we see a structure like this, like I'll draw one right now. This little caret I drew, that is propane. So how is it propane? All right. Each one of these vertices is carbon, and then you assume the rest of the carbon bonds are hydrogen. So there's going to be 1 here, 2 here, 3 here, and then we need 2 on this carbon, and then 3 on the terminal carbon. And then you end up with C3H8, which is propane. So we can go from the stick structure to the molecular structure that way. Okay, so what is organic chemistry? We have the branch of chemistry that focuses on carbon. So everything that's carbon-based, because we're carbon-based life, organic material. So why is carbon unique? It forms 4 bonds, and it's pretty nonpolar. So it's not going to, or when it's with most things, it's nonpolar. When it's with carbon-hydrogen bond, which is the backbone of everything, it's going to be nonpolar. And it's non-reactive too. So it's a good, stable backbone for a lot of our organic structures. And also it can form single, double, and triple bonds, and they can form together to create chains, rings, etc. So it's a very versatile element. So then you have hydrocarbons. So they contain hydrogen and carbon, hence the name. They are either aliphatic or aromatic. So aliphatic means it's a straight chain, and aromatic means it's in a ring that has alternating double bonds. But we'll see that later on. They're insoluble in water, very key thing, and that has to do with polarity. Now, most of the hydrocarbons that we're going to talk about here are nonpolar. There are some of them that are, such as, let's say, benzoic acid, right? Benzoic acid, which is benzene, so it looks like that, it has the aromatic ring, and it has an oxygen there and a hydroxide there. So it's a carboxylic acid functional group. We'll learn about those functional groups more next week. But this structure, benzoic acid, is actually a little bit soluble in water. So what happens is it's a weak acid. This hydrogen becomes deprotonated, and then you end up with benzoate. And then you can have a salt with it. You can have sodium benzoate, which then could dissolve in water. So some of these organics can dissolve in water. And they have polar and non-polar components. Now, clearly, the polar component is where you have all the oxygens. The non-polar component is where you have this mostly carbon, hydrogen, this benzene, right? The benzene part of the benzoic acid. It's going to be the non-polar part. So, yeah, it's insoluble in water. So you have aliphatic hydrocarbons, which are the ones that have a straight chain. So like the propane I drew before, right? That's a propane, that's a propane. Okay. You can have two types of these aliphatic hydrocarbons. The first one is saturated. So if you think of the word saturated, you think based on solubility, something is saturated. Like there's so much of it that no more can dissolve. Now for organic compounds, that's still true. It's so much of something. Now, what do you think these hydrocarbons are saturated with? Like, what does it mean to be saturated? Christina? Good. Saturated with hydrogens. Yeah, coming from the person who said that they don't know orgo.
I don't know orgo, I'm guessing.
You're guessing. Very confident guesser. Anyway, so saturated with hydrogens. But anyway, so we have, this is a saturated hydrocarbon. Then you could have an unsaturated hydrocarbon. So what this means is instead of the chain being completely saturated, meaning in every place that the carbon can bond to a hydrogen, it bonds to a hydrogen. Instead of that, we can have the formation of double bonds or triple bonds in the structure. So we can have a propane that turns into propene. So if we have a double bond. And what that looks like in the structure is you have C double bonded to another carbon, single bonded to a third one, like this. You have one carbon in the middle, two carbons here. This is called propene. So that's an unsaturated hydrocarbon. Then you can have another one that is an alkyne, and we'll learn about the names soon, but it's called propyne, which is basically like propane, but instead of a double bond, it's like propene. Instead of a double bond, you have a triple bond. So you have a carbon at the end here, one hydrogen, no hydrogens in the middle, and then 3 hydrogens on the end. So that propene is going to be C2H4. And there's also another compound that could be C2H4, which is ethylene. But yeah. Okay, anyway, that's a lot. Are there any questions? So basically, there's hydrogens and carbons that are making organic structures, and they're insoluble in water, they're nonpolar. Saturated means a lot of hydrogens and no double bonds. Unsaturated means a double or a triple bond where applicable. And it could be chains or rings also, and the chains could have branches, which we'll learn about that. Is it still considered an alkane? Yeah. No, it's a different functional group. So Christina had a good question. She said, instead of the carbon bonding to another carbon or another hydrogen, what if it bound to an oxygen? Is that still considered an alkane? And the answer is no. It's only for hydrocarbon chains. Now, when it does bond to an oxygen, there's going to be other functional groups that we can call it. It can be called an ester, an ether, a carboxylic acid, a aldehyde, a ketone, and an amide. There's just several of them. Okay, so here's the types of hydrocarbons. You have the alkanes. Then here's the way I remember it. So look at these words. They're very similar to each other. You have alkane, and these are just hydrocarbons, only hydrogen and carbon. So you have alkane, it has an A, right? Alkene has an E. E comes after A, so it's the second one. Alkyne starts with a Y, or not starts with a Y. The letter changes to a Y, meaning it comes after E, which is triple bond. So the hierarchy of unsaturation is alkane, alkene, alkyne. And the names of their specific type of hydrocarbon change the same way. They go from A to E to Y. So that's why we went from propane to propene to propyne. And then the aromatics, they contain benzene rings. And a benzene ring is what we just saw. It's the hexagon with alternating double bonds. Very key structure in chemistry, in organic chemistry. So any questions on that? Yeah, so the reason why they are aromatic, well, So these aromatics, they're volatile. And what that means is they have a low vapor pressure and they're easily, well, we learned about vapor pressure last semester. They are easily removed from their vapor and easily vaporized from their liquid, which means they're easily smelled, right? They easily can get through our nose. That's why they create this aroma. So yeah, good. So she says she has no work question.
I don't.
All right, so here's an example of different hydrocarbons, and they have generic formulas too. So and you can see this when you write them. And we'll learn about these prefixes in a bit. So you have ethane, ethene, ethyne. So eth means two. But we'll talk about it's going to be a new set of prefixes. All right. So I guess we'll go over the well, I don't like the order of this. I didn't really have time to modify these slides. Okay, we'll look at the order. So the order in terms of how many carbons there are. So the prefix of the hydrocarbon tells you how many carbons are in the structure, the longest chain. The longest chain. So for example, the first one is meth, right? Meth means 1. Then you have eth. The prefix eth means 2. Then you have prop, which means 3. Then you have bute, not but bute means 4. And then you have pent, that means 5, and then etc., like the shapes. So these are going to be, the first 4 are different prefixes that you do have to know that we did not talk about up to this point. And they're the prefixes telling you the amount of carbons in the longest chain in an organic hydrocarbon or any organic molecule. Or really mainly the hydrocarbons. So you can have, we'll talk about naming later. I don't want to confuse you. Any questions on that? Hold on, there's a question here. For unsaturation, does that mean that more hydrogen atoms could be added? Yes, it means that more hydrogen atoms could be added, and it could be reduced. So that's what it means. So like reduction means gaining of hydrogens, so it can be reduced more. And meaning the bonds could be reduced. The double bond gets what? And then it can be hydrogens can be added. And then Luke said pro what? I don't get it. Propane?
No, you said propene.
Oh, propene. And then propyne.
Yeah.
Yeah. They're all, sorry, what was that, Christina?
Propane and propyne are all different, right?
They're all different compounds.
Organic chemistry.
Yes. Sebastian, you have a question? Correct.
The suffix mean the number of hydrogen?
No. Hey, you got something wrong. Good. All right. So formulas. There's many. This is probably the toughest part of organic chemistry when you first start out. Is there are many ways to picture your molecules. If you read a textbook, no matter which source you see, it's going to be a little different. If you know all of them, it makes it easy. But they actually forgot one in this list. All right, so there's so many different ways of representing it. There's the structural form. This is propene. This is the structural formula, meaning you have the hydrogens drawn out, carbons, and kind of with the bonds, right? Then you have the condensed structural formula, like this. But you know what? This is not correct. This is not the condensed structural formula. The condensed structural formula is actually removing these bonds and it's C2H or C2, wait, no, CH2, CH3. They made a mistake here too, CH3. Wow, this text, wow, oh my God, these slides, like, yeah, look at that. That's a blatant error. It should be CH3. It doesn't want the bonds, no. Condensed structure means, and the reason why we call it the structural formula is because if we, an organic chemist would see this and be like, okay, this tells me the order of the carbon. So the first one has 2 hydrogens, second one has 1. That means that the first bond must be double in order to have carbon with 4 bonds, and so forth. Okay, so that's a good example you gave. So for acetic acid, we've seen acetic acid before. C2, H3, O2, and then we put an H in front of it. We sometimes write that as acetic acid. This is the molecular formula of acetic acid. There can be several structural formulas or several structures for one molecular formula. That's where we're going to get into isomers. So for this acetate or acetic acid example, sometimes we see it as this. Sometimes we see it as C3, CH, or no, it's C3, COOH. Yeah. Sometimes we see it as that. And this is because it's the this is the condensed structural formula. Because an organic chemist sees this and is like, all right, we have a methyl group, meaning it's CH3. Second carbon is double bound to an oxygen, also bound to a hydroxide group. And this makes it, this group right here is called a carboxylic acid functional group. So that's that. Okay, another example that we've already talked about was propene. So if you have, propene is going to be, or sorry, no, propyne. So propyne. So propyne is CH, we'll go here. All right, so propyne is CH3, C triple bond C, H. That's propyne. The formula is C3 H4, right? There's another formula for C3H4. We can just move this bond over here. So it can be C, double bond, C, double bond, C, like that, like that. That's also the same formula, different structure, different connectivity. So the point is that I use a simple example because there's some examples have 10 or 20 different ways you can write it with the bonding. So this is called an isomer, and we'll talk about different types of isomers in a minute. So are there any questions on the different types of forms that you'll see these in? And then there's the other one that we should talk about is that we already kind of talked about, is the carbon skeleton formula, which means the vertices are carbon and you assume the hydrogens. The nitrogens, oxygens, sulfurs, fluorines, whatever else you have on there will be written as their letter because you can't assume them in any way. Just like we saw for benzene and everything else. Once it gets to orgo, people start leaving. That's the best sound. So any questions on that? Okay, so now isomers. So we have a structural isomer, which is the propyne example that I used, where you can have the same exact formula, but a different molecule. So butane, you can have regular butane, which is a straight chain of 4 carbons, and then you have isobutane, which is you take a carbon from the end and you put it here and replace it with this hydrogen. This hydrogen goes on the end of here. So that makes isobutane. You could do that, that's fine. And then there's crap ton of other ways you can do structural isomers. Some questions on the exam or on homework might be, for the following structure, how many structural isomers are there? And it'll be something simple, like maybe a pentane at most. And I think for pentane, there's 3. Yeah, it's like resonance structures, kind of. And your bonds can move too. Yeah. So, okay, rotation about a bond is not an isomer. So you can, here's the thing. Single bonds can rotate freely. Double bonds can't. So think about it as, if you have like, watch my hands right here, right? Single bond, what can I do? I can rotate this. Double bond, what can happen? What's gonna happen if I rotate? It'll like twist and it'll like, it's energetically not favorable. And it's not gonna happen. Double bonds are pretty rigid. And triple bonds are even more rigid. And the bond strength increases, as we know, and the bond length decreases. So there's not really much room for movement. Only single bonds can rotate freely. So if you have a rotation about a single bond, then it is the same structure. Now this should be rotation about a single bond. That's very important, because if you have seemingly rotation around a double bond, meaning you look at, let's say, for example, C double bond, let's say we have an H and a Cl, and then we have a Cl and an H, and in another molecule, we did this, and then we switched the Cl and the H like this. These are isomers. It looks like they rotated around the bond, but these are called cis-trans isomers. This one is trans, this one is cis, because the substituent, the chlorine, the non-hydrogen substituent, is on the opposite side of the other one. Here they're on the same side. So those would be a type of isomer, which we'll talk about. Wait, no. Okay. All right. Any questions on that? And we're almost done. We'll do some homework soon.
Could you explain the difference between those two again? For some reason, I don't see your mouse, like when you're pointing to different things.
Oh, okay. Hold on. All right. So the difference between which one? The ones on the slides or the ones I just drew?
Ones that you just drew.
Oh, okay. So here we have, there's on the left one, the one I'm circling right now, there's two carbons double bonded, and on the opposite sides of one another, you have chlorines, which are non-hydrogen substituents, right? Here, on the right one, the chlorines are on the same side. The reason why they're considered isomers is because this double bond cannot freely rotate. So over time, you can't just have this chlorine switch over to the other side. They're kind of stuck in this position. That's what makes it a different molecule. It's called a trans isomer. And this one's called a cis isomer. So,
all right, that makes sense. Thanks.
Yeah, okay. Yeah, exactly right. So Christina had a question, why cis, why trans? So trans means opposite. So chlorines are on the opposite side here, and cis means same. Chlorines are on the same side here. Okay, question. So which structure is an isomer of the molecule shown here and not just the same structure? Yes. So I wanted to showcase how Pearson is, and look at this answer they put for their slides. They put it's C. It's wrong, because clearly that if you move this bond over here and move this bond up here, you get this. Yeah. So don't look ahead, because it might be wrong. Okay. So then we'll talk about this for the last thing for today. Stereoisomers. So stereoisomers are different molecules, but they're connected in the same way. Just like we saw for the cis and trans, the connections are exactly the same, meaning both of the chlorines are connected to carbons, which are the same connections, but they're oriented in a different way, and they can't be rotated back by a simple single bond rotation. So that's a stereoisomer. Then we have optical isomers called enantiomers. It's called, people say they pronounce it differently. Enantiomers, I just call them enantiomers, whatever. Enantiomers, they're a type of stereoisomer, and they are what we call non-superimposable mirror images. If you're like, Professor, what the hell does that mean? Look at your hands. Your hands are non-superimposable mirror images, because if you take a mirror, right? If you mirror image of one hand is the other, right? But if you try to superimpose them on one another, it's impossible. You can't like if you flip your hand to make it like that, it's still not the same. And then there's no way to superimpose your hands to be exactly placed exactly on one another. It's impossible. So that's what we mean by a non-superimposable mirror image. So here's an example of that. So we have a mirror image, and the mirror image is non-superimposable to the original image. So if you want to picture in your head of you rotating this molecule on the right to try to be superimposed perfectly with the molecule on the left. See how the blue ball is in the front? Blue one's in the front. It's impossible because the yellow is in the right place. Wait, hold on. Sorry, no, this mirror image. The mirror image, superimpose that with this one, it's impossible because the blue's in the right place, but the yellow and the other purple are in the opposite places, and it wouldn't work no matter how hard you try. Can you show us an example with the structural formula? Yeah. Of non-superimposable mirror images, sure. Like if you have, well, then you get into the wedges. So if you have this, if you have a wedge like that, that means it's into the page. And then if you have this, that means it's out of the page. So you have one going up, or sorry, one going up, one going down. And then, or let's say this is like a chlorine. And then you have one going this way, and it's like a fluorine. And then this way you have a bromine, right? So if you have this molecule, and then you have another molecule that has the hydrogen is going up, the chlorine is going down, bromines could be the same, doesn't matter, and the fluorine could be the same. These are two non-superimposable mirror images. You can't place this carbon, you can't place this molecule exactly on this one, but they connect the same. No, you can't. That's the thing. So that's a limit of the condensed formula, is you can't tell the difference between in the spatial orientation. What? Yeah, then you can. Yeah. But something like this, you can't, because there's specific three-dimensional angles and orientations. Okay, so then chirality. So chirality, any molecule with non-superimposable mirror image is chiral. All right, so what does chiral mean? Chiral means there's 4 different substituents bound to a carbon. All right, so any 4 different ones, as long as they're different. So even if something, let's say you have carbon and there's CH2, CH3, and then you have CH3. Technically, and then you have an H and you have a chlorine, right? This is chiral. Even though this carbon is bound to a carbon over here and a carbon over here, that means they're both bound to carbon. No, this carbon is different because this carbon has another carbon next to it. So this is considered a different group than this one, even though they're both carbons. So this would be considered a chiral molecule. And then you have a chiral center, which means the center carbon that is bound to 4 different things. So the pair of the isomers is called antanomers, the ones that are non-superimposable mirror images. And this is a great example with the hands here on the bottom, where you see the same kind of thing. All right, any questions on that? No? All right, so we'll talk about this part and then we'll stop. So here's optical isomers of 3-methylhexane. So hexane is 6. So you have 1 carbon, 2, 3, 4, 5, 6. And then you have the chiral center. So the chiral center is the carbon that's bound to 4 different things. Now on one side you have a hydrogen. The second side you have 2 carbons. The third side you have 3 carbons. So there's different groups on each side. And the fourth side you have just 1 carbon. So all 4 of these different things, or all 4 of these things are different, all the substituents. And on the other antanomer, you have, it's clearly a mirror image and it's non-superimposable. So that's how that works. All right, so then we're going to talk about plane polarized light. And basically what we can talk about here is the phenomenon having to do with aromatic structures. So one thing that they have, as we already talked about, they produce an aroma. But the second thing is that they're optically active. So what this means, and it's also true for chiral centers and aromatics, is that they will rotate plane polarized light in a certain direction, right? Now, don't really go, we're not gonna go too far in depth of it. And we can, based on the different type of enantiomer, if it can rotate light one direction versus the other, we call them D and L. So L means to the left, I just call it left. So it's levorotary, which means to the left, and you have dextrorotary, which means to the right. So L and D isomers you can have. And when in Orgo, you go crazy in depth on those. We're just gonna be scratching the surface. And we can say for each stereoisomer, is it going to be an L stereoisomer or a D stereoisomer, based on which way it rotates plane polarized light. I can't tell. You can't. How can you tell? Well, I guess it's lit to the left. I don't know. What does it look like to the? I don't know. You can't tell from the picture, can you? Anyway, okay. So then we'll stop with this conceptual question in 2 slides. So if you have so most of the mixtures you have, so if you create these compounds, right, they're created the same exact way in the synthesis, in the organic synthesis. You have a racemix, or racemix, I call it racemix, because that's how I was taught it. A racemix structure, or mixture. That means there's a mixture of both the D enantiomer and the L enantiomer. This means the substance itself does not have, or does not rotate the plane polarized light. And if it's a non-racemix structure, you can tell based on the amount that it rotates light, how much of the L and how much of the D enantiomer is there. But again, this is very brief. We don't want to go crazy in depth here. So chemical behavior of enantiomers. If you have different enantiomers, they react differently with everything. They would bind differently. They react differently. So some enantiomers, there's drugs out there that the enantiomer kills you and the L kills you and the D doesn't. And the D is like aspirin. So it's very very high, big implications, the stereoisomerization. So and you can see that based on that, if you were to bind to an enzyme, you need to have a very specific orientation of binding to an enzyme. And one enantiomer has that orientation and the other one doesn't. So it's gonna be a completely different molecule. So yeah. Here's the last one. So which of the molecules exhibit optical isomerization? So which one of them can be an optical isomer? Meaning which one of them would rotate the plane polarized light? And it could either be aromatic, which none of these are rings, or it could have a chiral center.